last part of Chapter 9, and that is modern measurement. In that last little section of 9.3, the first part there, we talked about kind of the traditional way, some of those things that have been around for a long period of time. Now we're going to be looking at things that haven't been around as long. Some of these things have been around for a little while, but weren't really used for weather or were more recently used. And one of the first ones is the automatic weather station. This allows atmospheric conditions to be monitored without a meteorologist on the site. If you remember the Stevenson screens from the last video, this is very similar to that, only really the only difference is here we have something computerized that transmits data to some other place so that the meteorologist doesn't have to go out there and physically take readings. So yeah, these are they're automatically reporting weather stations, and there are many of them around the U.S. The National Weather Service uses probably hundreds or thousands of these. And then we also, in some areas where manually monitored instruments would be difficult, the Sahara Desert, tops of mountains, at the poles, where people just don't go very often. These automatic weather stations provide a lot of practical use there. Some automatic weather stations have sensors that detect special weather conditions such as fog. Although the first automatic weather stations needed to be connected to an electrical power line into a telecommunication line because cell phones and batteries weren't that good yet. Now we have satellites, cell towers, a lot of wireless features. Batteries are much better, so that if there is electronics, that they can survive for a much longer period of time on that. Many automatic weather stations, including those at airports, include a transistometer. And this is a device that measures visibility. And visibility is just the furthest distance at which objects can be distinguished. So fog can play a big role in visibility there, or even low-flying clouds. Basically the source and receiver are mounted on two towers at a specified distance. The source fires a laser, which is light, so it's going to be affected by anything that affects light, which is exactly what would affect our visibility. And if there is anything, that receiver will receive whatever light gets through, if any. And then they can make measurements based off of that. One important group of automatic weather stations are the automated surface observing systems, used extensively by the National Weather Service. Over 900, that's how many there are located around the United States, mainly at airports, but and many other places as well. Gives up-to-date weather reports to the airports as well as to meteorologists that would just want to know. Many times it's useful to know what's going on in the upper atmosphere. And the only way to do that is to get instruments up there, and for a long time, weather balloons have been used for this. These are unmanned helium or hydrogen-filled balloons that have instruments attached to them. They go up high, take readings. In the old days, they would just fall back to Earth, and they would record the readings from what fell. Nowadays, they can probably transmit those readings and stay up there a lot longer as a result and give us more readings than before. Kind of like a weather balloon, but using different technology, is the radio zone. Transmitting meteorological data from balloons to weather stations below our radio zones. Sorry, I got ahead of myself. But the radio zones are what's doing the transmission there. A typical weather balloon rises about 1,000 feet per minute, reaching an altitude of almost 22 miles. During this ascent, the decreasing air pressure will allow the balloon to expand from 6 feet wide to almost 20 feet. I've seen some people doing weather balloons before, and when they fill them up, they really don't look like they're inflated at all, but they have enough lift that they go up high. And the reason for that is because they will expand. They need to allow room for the expansion of the gas in the balloon when it gets up to that top altitude. Once it gets too far, the balloon pops because the material can't stretch anymore, and this brings the radio zone with a parachute back down to Earth. And they are found and sent back to the National Weather Service to be repaired and reused. And this is where I was getting ahead of myself. Similar to the weather balloon, but utilizing rockets, are sounding rockets, small, inexpensive rockets that can launch light instruments up to several hundred miles up. So this is going to get way higher than weather balloons, but it's the same idea, just getting instruments up to those high altitudes where the data could be useful for us. Getting such things as temperature, air pressure, solar radiation. They've also been useful in studying the auroras, borealis and australis. To measure the distance from the ground to the base of clouds, meteorologists use something called a ceilometer. Ceilometer, I always say it wrong. Ceilometer. A ceilometer shines a laser upward. Think ceiling, the ceiling of the cloud, so it's a ceilometer. It shines a laser beam upward. If clouds are present, the beam of light reflects off the clouds. Because after all, what color are clouds? They're usually gray or white for the most part. Some get so dark that they could be considered black or really, really, really dark gray. Either way, some of that laser is still bounced back down, and they can figure out the distance from the ground to the base of the clouds. Before the use of lasers in this, they would actually have to use math. They would have to use triangulation and comparing triangles, similar triangles, to figure out how high up the base of clouds were. So the ceilometers make it a lot faster. They do a lot of the math for us. And then one of the most useful ones, you've probably seen this on the news channel, and that's radar, which stands for radio detection and ranging. This detects objects and measures their distance. Well, it was developed in World War II pretty much to keep track of flying aircraft, both friendly and enemy aircraft. And a little while after that, some meteorologists realized it can actually be used to help with weather. So they tweaked it just a little bit, and they developed what's called the Doppler radar. You might hear the phrase NEXRAD, which stands for Next Generation Radar. Doppler refers to a physics effect that can happen with moving objects. It could also be called the WSR-88D, Weather Surveillance Radar, or from 1988 Doppler. This can measure both precipitation and the speed and directions of wind. Because of their densities, the different densities of air and water and such, it can actually show up on a radar. And you may have seen that on the weather station when they bring up the Doppler radar, usually if it's raining or to try and show where clouds are and such. So very useful later on for weather. The weather satellite, just basically it's specifically used for tracking weather, dedicated to tracking different events as far as weather goes and reporting back down to Earth. Been very useful for that. Surface weather charts. These are maps that give a summary of the weather conditions throughout the entire country at a single point in time. You can actually go online, and I believe it's the National Weather Service. You can find some of these, and it's usually based off of those automatic stations, and they give a lot of conditions there. And it's a summary of temperature, pressure, wind direction, any precipitation. And that could be, these surface weather charts can be used to create a station model. These are conditions at each weather station represented by groups of numbers and symbols. Different symbols mean different things. The location of the numbers are either temperature or pressure. So used together there. And then on some maps, and if you look in the book on page 295, you would see some examples of not station models, but isobars. These are curved lines of equal pressure. Represents air pressure that have been recorded by the weather stations. And they just link those areas of same pressure, showing lows, highs, how quickly it spreads out, all that kind of stuff. Isotherms are broken lines that connect stations of equal temperature. So it's not just the equal temperature there. So this is, as opposed to pressure, this is focusing on temperature. Notice that we talk about bars as measurement for pressure, and we have isobars on the map. Thermometer, temperature, broken lines that connect stations of equal temperature. So these are lines that connect the separate stations there. And then we can use all this information to make those weather forecasts. These are just those predictions that we've kind of been alluding to over the course of this section. And one of the most useful tools in allowing us to do those forecasts are supercomputers. Extremely powerful computers capable of rapidly performing complex calculations, keep track of weather conditions all over the world. They can be programmed. This data is this, if this piece of data is this, it can spit out a lot of information very quickly. And up until that point, we just had individual meteorologists looking up the information and doing their best with just a smaller set of data. And supercomputers have allowed them to use way more data points and become even better at predicting weather. Now, there's still a lot that goes into the weather. There's a lot that they can get wrong from time to time, After all, there's probably a lot of adults that can remember, maybe you remember, that you're wearing sunglasses on a day when the weatherman said it's supposed to be downpouring. So they do get it wrong, but it's a lot better than it used to be, and that is the end of chapter 9. So we will be doing a reviewing class here soon and finishing up, doing the test and everything to finish up. So go answer the science video question for this section, and we're done.